Hi guys, my name is Puneet and I'm a PhD student in Santa Clara University. I'm the author of Clustering of Point-to-Point Ethernet Transmission Wireless Backhaul Links. So let's start. All right, play the slideshow. All right. So, what is the agenda? The agenda is to actually explain what is clustering first. And you guys might be wondering, like, how is it different than normal bonding of interfaces like LACP? Then we will talk about the normal clustering, what is the missing part here in the existing clustering solutions. And then we will talk about the challenges, which we have overcome in the missing parts. And what is the clustering algorithm we are presenting and what are the results and then conclusion. So nothing much. All right. So what is clustering? So clustering is a way to aggregate links while still segregate the control management and data plane. So it's a kind of tricky definition. So let's imagine you have like three interfaces, and don't go into wireless or anything. Just go into wired one. Okay. So you have two devices, device one and device two, and you have three interfaces basically connecting to these. Now you can do a LACP configuration between these two devices, right? So that's fine. So you have an aggregated link now. But how do you segregate whether this is a control plane traffic or management plane traffic or data plane traffic? You don't. And that is important because let's say you want to prioritize your ACK, TCP ACK, then what would you do? Well, the packet scheduler will basically just see a next hop interface identifier, and basically just the network stack will just send the packet out. That's where the clustering comes in. The clustering is basically an aggregated link solution which basically segregate the control plane and management and data plane. So normal clustering solutions will have like dedicated VLANs to that. So one VLAN will actually have a control plane VLAN, then a management plane VLAN and data plane VLAN. So this is what this particular thing is. Another thing is that if a TCP flow changes in this link, which we talked about, the two devices with three links, LACP, then the TCP will break, and then you have to pay a 1 RTT cost of connection establishment. The entire drama of SYN, SYNAC, and ACK. So this is why clustering is basically a wonderful solution in my eyes. So let's see what are missing, and basically, how can we do that? So this is a physical topology. Let's just imagine like you have four wireless links. Every link has a 1 Gbps of data rates, right? So theoretically, this is 4 Gbps, but in not always you will achieve 4 Gbps in clustering. So in our solution, we have a cluster which is runs on the DM, runs as a daemon and on the radios, and for the upstream and downstream devices, they will look like a single link. They will also have a failure mechanism in which the link is dead. All right, so first is how does the cluster forms in our solution? So cluster forms in our solution by basically, this algorithm, which is called like primary radio. So when you have zero radio in the cluster, basically any radio which joins the cluster will actually be declared as a primary radio. Now, if you have radios in the cluster already, then any newly added radios, which has a higher priority, will actually be added as a primary. Now, who assigns priority? It's the user configure thing. And the reason why we actually chose to have a user configured thing is because some people wants to have let's say you have a very expensive hardware. I'm not going to take company's name because that will be copyright infringement, but let's say you have a very expensive radio and another radios are not that expensive, and another non-expensive radio joins the cluster first, so it will become a primary. Now the expensive radio comes in, so if you don't let user to configure that as a primary, then the non-expensive radio will actually carry the most of the traffic. So yeah, this is what the algorithm was. So now another thing is the bootstrap configuration. So the thing is like clusterings don't allow links to go down and come back because it will break the TCP connection. So what they do is basically they have a bootstrap configuration, which is the default configuration you assign to a unit, and when the unit comes up, it will have those configurations and basically work as it is. So this is what a bootstrap configuration means. So in our solution also, every radio will have minimal bootstrap configuration. First is basically, this is the header for this one. So it will be sent to each radios as a multicast message in every 3 seconds, because if we want to change, let's say, some kind of configuration on any radio, this is the message which is going to be used. So what are the different types of cluster interfaces? So first one is the individual routed mode, which means that each radio will have its own IP, and each radio will be capable of doing L3 routing. Another one is the spanned Ethernet channel LACP, which means that they will actually, have a LACP interface among these four radios, and this will be the L3 link for the routers of northbound and southbound. And obviously this spanned Ethernet channel link will have one IP, and all these link inside this spanned Ethernet channel will actually act as a L2 links. So yeah, so how do we monitor radios in this, like in the clustering? So we basically have placed a health which can be checked, and this is done by clustering keep alive message. And the keep alive message format is given like on the left hand side. You can see the cluster message header, which defines that the message is basically for clustering. Selection info type is the component which we will be looking into, and the radio info component which we'll be looking into. All these message types we will be looking into now. So, oops, yeah. So okay, so this selection info component message you can see on the figure 8 is the it contains three things: serial number of the unit, and the priority, and the role. By role I mean is like every clustering solution will have like dedicated proprietary, which means that every this is like a principal in the school, and it will monitor every TCP connection coming in, and if a TCP connection requires rerouting or it requires transfer, it will basically give it to the other unit. The another one is the organizer and forwarder. Organizer is basically the one which basically tells the proprietary that like, hey, I have a TCP connection. I have a packet which doesn't belong to me. The TCP established, the connection establishment did not go through me. What should I do with this packet? So proprietary will actually tell that, hey, give it to this forwarder, because this is the guy who actually was involved when the TCP SYNAC was going on, and he has the connection state. So basically just give it to this guy and it will route it. So this is what basically these roles mean. The radio info component message format has four things: mode operation, which means if it's a individual routed interface or if it's a spanned Ethernet channel interface; the radio type, which means that whether it's a proprietary organizer forwarder; the SNR, which is basically the SNR for this particular link; and the load balancing weight. Load balancing weight is basically a new parameter which we introduced. It's used for load balancing. So yeah. So how do we replicate the data path connection state? What I mean by that is like, for example, like I just gave you a scenario where organizer will tell you that this particular radio has received a packet which did not get established. The TCP connection did not get established based on this. So what should he do with this packet? So proprietary will tell you like, hey, just pass it to this forwarder, right? So when he does that, it also replicates the data state, so that next time when the packet comes to this forwarder, it doesn't ask and do all this drama of asking organizer and hey proprietor, please tell me where the packet should go. The forwarder will actually do it by itself. So this is what it means. It's this type of message exchange basically done by the message type of cluster per layer info. And since we have a time limit here, I mean I cannot go to each and every message in detail, but the paper will have all these details. So this is our load balancing algorithm. It's very sophisticated one. So it's based on the hash of source and destination IP and the number of links. So as you can see, this basically does an XOR. So what I mean by that is, if you have a higher number of the first octet of IP in source or in destination, the chances of you getting the hash value is lower, because it actually does the mod of number. So you will end up in like the initial links. So that way the initial links will be filled first, and then the rest of the links. And we want it this way because generally when any unit gets added to a cluster, this will become like a proprietor. So proprietor should handle most of the traffic, so that if any packet comes to any radio, this entire asking of organizer from forwarder doesn't happen, that where should I send this packet to. Okay, so these are the roles. I already explained it to you, but this is what like these are additional thing which here is the backup proprietor, which basically is the same thing. If the proprietor goes down, the backup proprietor takes over. But here's the thing: the connection state is a very expensive process. You ask any network admin, they will tell you like it is the most expensive process runs on their machine. So actually, I wouldn't say I would say one of the most expensive process runs on the machine. So it would be really foolish to copy the entire connection state from proprietor to backup proprietor, but it does it in chunk so that it relies on this faith that if the proprietor goes down in middle of sending this chunk, then it has to reshuffle the entire TCP connection, which usually doesn't happen. Though that's why we like it would be stupid to just copy the entire TCP connection state from proprietor to backup proprietor. Anyways, so this is what a very important slide. This is like the meat of this entire paper is like how the data packet flows. So you can see like from radio one, on the left hand side, and let's just concentrate on TCP first. So there is a SYN packet going in the red arrow. You can see from the switch all the way to the access point, and the SYN packet goes from the station to the access point and basically goes to that. Now, the right hand side switch decides to send the SYNAC on the radio too. Now, this is the forwarder, and it asks to organizer the where should I send this packet to, because the connection establishment did not go through me. So what it does, it basically it sends to the proprietor, which is the first radio, the SYNAC, and the SYNAC actually goes back to the switch. And here's what now the data the connection replication has happened at this point of time. So next SYNAC, if it reaches for this connection to radio 3, it will not send it to the station of the first link. It will basically just transmit it by itself. So yeah, this is what I meant uh, by the rules. Anyways, so the UDP is a different scenario because UDP does not have the state, and it can change the port, the source and destination port. So it's really not like very reliable in terms of 5 tuple. If you track them that this connection did go through me or not, it has like a query system, which means that hey, uh, did you see this port and this connection, the destination port and the connection? Then it will tell you that yeah, I did see that, and this actually went by me. So it basically forwards to that first radio and it goes through that. Now this is very very important for a protocol like Quick, because Quick runs on UDP, and if you don't have this kind of mechanism, then what will happen is that Quick actually has a multi-stage key exchange protocol, which means that it exchange keys like a lot of times. And if your link changes, then this key will actually trigger to go through one RTT all the way back. Also, it will trigger like path validation packets in Quick. So this is a unnecessary, bandwidth exhaustion. So this can save that. So this is our simulation model. As you can see that we have a multi-layer simulation model. And the reason why we chose this one is because, these WAN, LAN and WLAN, they are like software objects. So we can create like any number of them. And those simulates like a wireless backhaul link. And then we can just run our experiments and collect the data. Now, if we also have like a loop back, and these functions which write physical reliable and write physical, they all like based on sockets. So it's like a normal socket read and write. So this is our results. As you can see, like without clustering, we have a very less TCP throughput, but with clustering, we actually like almost quadruple it, and we have a number of links are like 4. So and it's pretty much constant, like for 5 seconds. So we can actually like determine that this solution works, and if you aggregate the link and it doesn't break the TCP connection in between if some packet decides to go through some other radio. So this is our conclusion. With the help of proposed clustering algorithm, connection can move easily with different entities like we saw. And in case of failure, connection can still be transferred without breaking the connection end to end, which we saw. Throughput increased, which we saw, and traffic is load balanced by our load balancing algorithm. So this concludes my presentation. I hope you enjoyed it. Thank you.